Welcome, my friends. In this video, we will solve trigonometric equations related to real-world situations. In this first problem, we are told that the height above ground of an individual on a Ferris wheel is described by the equation h of t is equal to 18.6 minus 16.5 times the cosine of 2 pi over 5 times t. H of t represents the height above the ground in meters, and t represents time in minutes. During the first 5 minutes of the ride, when will the person be 11 meters above the ground? Let's take a look at a Ferris wheel. We know that on the Ferris wheel, people will be going around and around and around and around. And at some point, they will be 11 meters above the ground. And this actually happens at 2 points on one revolution of the Ferris wheel. For example, if this was 11 meters above the ground, you would be at 11 meters above the ground right here and also over here. Additionally, depending on how fast the Ferris wheel is rotating, we might actually have several rotations in the first 5 minutes where we are 11 meters above the ground. Maybe it only takes 1 or 2 minutes to make one rotation, so we might have several times in the first 5 minutes of the ride where the people will be 11 meters above the ground. Let's take a closer look at the equation. The equation is 18.6 minus 16.5 times the cosine of 2 pi over 5 times t. We are asked to solve for when the person will be 11 meters above the ground. H of t represents the height above the ground, so we must set h of t equal to 11. From here, we would like to solve for t, so let's isolate the cosine function to one side of the equation. We can start by subtracting the 18.6 from both sides of the equation. 11 minus 18.6 will give us negative 7.6. So we have negative 7.6 is equal to negative 16.5 times the cosine of 2 pi over 5 times t. Let's divide both sides by negative 16.5 to cancel the negative 16.5 on the right-hand side of the equation. We will be left with positive 7.6 over 16.5 since the negatives cancel on the left-hand side, and cosine of 2 pi over 5 times t on the right-hand side. We know that the way to solve for the angle related to a cosine function is to take the inverse cosine of both sides. We have the inverse cosine of 7.6 over 16.5 on the left-hand side, and the inverse cosine of 2 pi over 5 times t is just 2 pi over 5 times t. We want to solve for t, so let's multiply by the reciprocal of the coefficient on t. If we multiply both sides by 5 over 2 pi, we will cancel the 2 pi over 5. We will be left with 5 over 2 pi times the inverse cosine of 7.6 over 16.5 is equal to t. If we type inverse cosine of 7.6 divided by 16.5 and we make sure that our calculator is in radians, we will get approximately 1.0921. So altogether, we have 5 over 2 pi times 1.0921 is approximately equal to t. I say approximately equal to because this decimal goes a lot more than just 4 decimals. If we type this into our calculator and make sure that we have parentheses on the 2 pi in the denominator, we will have t is equal to approximately 0.87 minutes. At just before 1 minute, we will be 11 meters above the ground. Now, 0.87 minutes is most likely not the only solution. If we think back to our Ferris wheel, recall that we said there are 2 points on one rotation of the Ferris wheel where we would be 11 meters above the ground. So perhaps this is 11 meters above the ground, and we would reach that point at 0.87 minutes. We would also reach that same height above the ground going back down, so perhaps over here. There would be another time on one rotation of the Ferris wheel that we would be at the same height of 11 meters above the ground. And also, depending on how long it takes to make one rotation of the Ferris wheel, we could perhaps be back over here within the first 5 minutes. And then back over here again on the way back down, we would again be at 11 meters. So there are perhaps going to be a few more solutions. So how do we find those solutions? Well, I hope you remember that inverse cosine will always give you an angle on either quadrant 1 or quadrant 2 on the unit circle. But there is a second time when we would have the exact same x-coordinate on the unit circle, either in quadrant 3 or quadrant 4. In this case, inverse cosine of 7.6 over 16.5 asks cosine of what would give you 7.6 over 16.5, whatever that ratio equals. Well, it turns out that cosine of about 1.0921 radians would give us an output of 7.6 over 16.5. 1.0921 radians is somewhere in the first quadrant. How do I know that? Well, 1.0921 is somewhere between 0 and pi over 2. Pi over 2 is half of pi, or approximately 1.5 to 1.6, so 1.0921 radians would be somewhere in quadrant 1. So we have some angle in quadrant 1, which would create some x-coordinate on the unit circle, which would represent cosine. There is another time on one revolution of the circle that the x-coordinate would be the same, and that would be in quadrant 4. So perhaps if this was our x-coordinate, there would be an equivalent x-coordinate in quadrant 4. How can we find the angle corresponding to quadrant 4? Well, in our case, we are 1.0921 radians into quadrant 1, or above the positive x-axis. If we go 1.0921 radians below the positive x-axis, we will have another angle that has the same x-coordinate in quadrant 4. The way we can find this is by taking 2 pi and subtracting our angle of 1.0921. So if we take 2 pi and subtract 1.0921, which is inverse cosine of 7.6 divided by 16.5, we will get approximately 5.1911. This is the angle in quadrant 4 that has the same x-coordinate as 1.0921. If we multiply this out, we will get approximately 4.13 minutes. So the second time that we reach 11 meters above the ground on the Ferris wheel would be after 4.13 minutes. If you want to think about the picture again, this would be coming on our way back down from the top of the Ferris wheel. So the first time, at 0.87 minutes, we would be going up the Ferris wheel. And the second time, when we're coming down the Ferris wheel, where we have the equivalent height of 11 meters, would be after 4.13 minutes. Now there would be another time when we're going back up the Ferris wheel another time, where we would be 11 meters above the ground. But based on the numbers that we have here, it's unclear if that will be in the first 5 minutes of the ride. Let's find out. If we took 1.0921 radians and we added 2 pi, we would have an angle that is coterminal with 1.0921 radians. This would be the next time when we would reach 11 meters going up the Ferris wheel. So let's plug that into our calculator and see what we get. So first we need to take this angle and add 2 pi. So we have 1.0921 plus 2 pi. So this is the coterminal angle with 1.0921, which we would also be 11 meters above the ground. Now we need to multiply this value by 5 over 2 pi. So let's multiply that value by 5 over, and I need parentheses on the 2 pi. If I press enter, I will get 5.87 approximately. Remember, this is a value in terms of minutes, so this says the next time we will be at 11 meters above the ground would be after 5.87 minutes. 5.87 minutes is after the first 5 minutes of the ride, so that is not a valid solution. Our only two solutions are after 0.87 minutes and after 4.13 minutes. Okay, let's try one more problem. A projectile is fired from a cannon with an initial velocity of v sub 0 at an angle of elevation of theta. R of theta is the horizontal distance the projectile travels in feet. If r of theta is equal to v sub 0 squared times sine of 2 theta divided by 32, and v sub 0 is equal to 160 feet per second, what angle theta, in radians, should be used to hit a target that is 435 feet away from the cannon? So we have a cannon that is firing a projectile, most likely a cannonball. We want to know which angle should we set the cannon at so that it will hit a target that is 435 feet away. Now perhaps there could be more than one solution. Maybe there is a smaller angle that will take a more direct path right to our target. Perhaps there is also another angle that is larger that would take a more vertical path to our target. We'll find out through our problem if there is more than one solution. Our equation is r of theta is equal to v sub 0 squared times sine of 2 theta divided by 32. R of theta is the horizontal distance that the projectile travels in feet. We would like to hit a target that is 435 feet away from the cannon, so that means that r of theta must be equal to 435. We also know that v sub 0, the initial velocity, is 160 feet per second. So we can plug in 160 for v sub 0. We would like to solve for theta, so let's start by multiplying both sides of the equation by 32. The 32's will cancel on the right-hand side, and we have 32 times 435, which is 13,920 on the left-hand side, and 160 squared, which is 25,600 times sine of 2 theta on the right-hand side. Dividing both sides by 25,600, we get 0.54375 on the left-hand side and sine of 2 theta on the right-hand side. The way that we solve for an angle and a sine function is to take the inverse sine of both sides. On the left-hand side, we have the inverse sine of 0.54735, and on the right-hand side, we have 2 theta. Let's divide both sides by 2. We have the inverse sine of 0.54735 divided by 2 is equal to theta. If we plug in the inverse sine of 0.54735 into our calculator, we will get approximately 0.5792. So that means that theta is approximately equal to 0.5792 divided by 2. If we divide by 2, we will get that theta is approximately 0.29 radians if we round to the nearest hundredth. Now, as mentioned earlier, this is most likely not the only solution. This is most likely the smaller angle that's going to take a more direct path to our target. There's going to be a second, larger angle that's going to take a more vertical path to our target and still hit the target that is 435 feet away. So how do we find that angle? Now recall that inverse sine will always give you an angle that's either in quadrant 1 or quadrant 4 of the unit circle. Inverse sine of 0.54735 is asking sine of what gives you a y coordinate on the unit circle of 0.54735. If we take a look at our unit circle, we know that the angle of 0.5792 radians puts us somewhere in the first quadrant. We know that the y coordinate must be 0.54735, so that might be right around here on the unit circle. But there is another time on one revolution of the unit circle that we will have the same y coordinate, and that will be in quadrant 2 over here. So if this point at the angle of 0.5792 is a solution, we should have another solution at pi minus 0.5792. We are 0.5792 radians above the positive x-axis for our first point, so that means we must be 0.5792 radians above the negative x-axis for our other solution. The way we find this is by taking pi and subtracting 0.5792. Now 0.5792 is the same thing as inverse sine of 0.54735, so we can find the answer by taking pi and subtracting that. The result is 2.5624 radians. 2.5624 radians is another angle that also has a y coordinate on the unit circle of 0.54735. If we type this into our calculator, we will get that theta is approximately equal to 1.28 radians. This is the second, larger angle that the cannon could shoot to still hit the target that is 435 feet away. At an angle of 0.29 radians, we would have a more direct path to our target. At an angle of 1.28 radians, we would have a more vertical path to our target. Here is an image that displays the two angles. The larger angle of 1.28 radians could reach the target that is 435 feet away. But the smaller angle of 0.29 radians would also reach the same target. Alright my friends, that finishes this video related to trigonometric equations and story problems.